So we've talked about how to fit means as outcomes models or models with level 2 predictors using LME4, and it was pretty straightforward. The more complicated thing is thinking about effect sizes, or R squared, and that's what we're going to talk about in this video. So R squared in ordinary regression, or ordinary least squares regression, is a pretty straightforward concept. It's the proportion of outcome variance accounted for by the predictors. In HLM, this gets quite a bit more complicated because the variance is partitioned into level 1 and level 2. We don't only think about our total variability in our level 1 observations, we also think about the level 2 variability. So how do we think about R squared when that's the case? And the literature actually has a lot of attempts to conceptualize R squared in HLM, and there's actually a lot of different people who would tell you a lot of different things about the correct way to do it or the best way to do it. And it's been a little bit of a mess until recently. This paper by Reitz and Sturba, which you talked about, was a really nice attempt to unify a lot of these ideas and develop a framework for us to think about R squared and HLM that can give us sort of a common language about it. And it's not the most straightforward paper in the world, but it is a big step forward in terms of hopefully getting everyone on the same page in terms of how they think about R squared and HLM. So when we have level 2 predictors, there are sort of 4 components that we could think of as being of interest, at least that you discussed in your lecture. And these are the total variability of the outcome, and this is both between and within cluster. The total level 2 variability of the outcome, which is the between cluster variability only. Then you have the variance accounted for by the predictors, and the variance unaccounted for by the predictors. And that last one would be like residual after the variance accounted by the predictors is taken into account. Now, we're not talking about level 1 or within cluster variance because that's unaffected by level 2 predictors. It'll be a constant across any model that only includes level 2 predictors, and so it's not really of interest to us now, although it will be when we think about models that include level 1 predictors. So you talked about these 4 different types of R square in lecture, and I could see how this might be very confusing and overwhelming, and it was for me when I first started looking at it, which is really only within the last week or two when Dr. Chen pointed this paper out to me. And so let's try to break down what each one of these is doing. And so the R squares have a superscript and a subscript, and the superscript is in parentheses, and it's only in parentheses to differentiate it from the exponent, 2. But you could think of this as being the superscript, and this as being the subscript. And in each case, the superscript refers to a numerator, and the subscript refers to a denominator. And they correspond directly to these different ideas. So in the models that we're looking at here with level 2 predictors, F2 is the explained level 2 variance, and T is the total variance. M is the unexplained level 2 variance, and B is the between cluster, just the total level 2 variance. So again, we have F is what the predictors are accounting for. F is the variability explained by the level 2 predictors. T is the total variability in the outcome. M is the residual level 2 variance that's not accounted for by the predictors. And B is the total between cluster variance that includes the variability that's accounted for by the predictors. And so we're going to talk about the sort of interpretations of these different R squares, but it helps to first get a quick refresher on the types of model notation because we can actually refer to these to help us think about what these different R squares are doing. And this can help us think about what they mean. And maybe this can also help us remember how to do the 2 different types of model notation. So you have the combined model notation where everything is put into one model, where you have your outcome variable, P affect ij in this case, predicted by the grand mean, gamma 0, 0, and then gamma 0, 1 times the predictor activity. And then you have your mu 0j's, which are your cluster mean differences, and your residual. Then you have the separate model notation. And in the separate model notation, the first thing you're doing is predicting the cluster means, which is the beta 0j. Here we have gamma 0, 0, which is the grand mean, plus the effective activity, and then the cluster mean differences predicting the cluster means. So that's the first model, the level 2 model. And then the level 1 model below it, you have your level 1 observations being predicted by beta 0j and then a residual. This is why it's called a means as outcome model, because you really only have the cluster means predicting your outcome, but you do have a variable that helps predict your cluster means. And that's what the separate model notation is showing us here. And so we can use this to sort of think about the different R-squares and what they mean. So the R squared with F2, which is the variance explained by the predictors, and then T, which is the total variability, we could think of sort of as like an R square for the total combined model. So it would be the R square when we think of the full model all at once. We can think of the R squared MT as the unexplained variability out of the total variability. And if you think back to last week, this is very similar to the idea of ICC. In fact, this is sort of like a partial ICC because it's the residual unexplained variability after accounting for the predictors. So it's sort of like an ICC that's left over after we have the predictors involved, the level 2 predictors. So it's like the remaining ICC. So if the predictors accounted for all of our variability in our cluster means, then this might go to 0. That's unlikely, but just conceptually, that's what it would mean. So R squared F2B is the R squared from the first part of the level 2 model. So it would be like the R squared just from this model here. It would ignore this part, and it would just be the R squared of activity predicting the cluster means. And then finally, R squared MB is just 1 minus that. It's whatever remaining residual there is out of the total cluster mean variance. So this is a lot. This is a lot of sort of information to digest, and this is a pretty new framework for thinking about R square. But fortunately, the crack programmers in R have already started working on a package that implements it for us. And this actually isn't on the CRAN network yet, which is where the install packages function looks. It's not on the official R package repository yet, but that's because it's still in development. And from what I can tell, the only reason it's not been sort of fully released is because there's some bugs to work out in its data visualization, but the actual number crunching is doing what it's supposed to be doing, so we can use it. So to access a development package that's on GitHub, you first have to install this remotes package. And then from inside the remotes package, there's this install GitHub function. And then you can just install the package directly from GitHub. And this will look a little different than when you're installing from install packages, but it might ask you if you want to update some other packages. And if you try to do that, it might give you some grief. You can just skip updating the other packages and just directly install this package as it asks you to do that. And we'll look at this together in lab. And then once it's installed, you can just load it up like any other package. And so here I'm creating an R squared object by calling the R2 MLM function on my my LME4 object, my HLM. And you don't have to do this. You can just print this directly, but it's going to give you 3 things if you do that. It's going to give you a table of decompositions, which we're not that interested in here. It's going to give you your R squareds, and then it's going to give you a plot. And the plots are what seem to be a little bit buggy. Let me show you what happens if you call this. So I'm back in my R console now. I have R2 MLM loaded up. So if I just run this command, see it's going to give me this table of decompositions up here, and this table of R squares, and the table of R squares is what we're really interested in. And then it's also going to automatically output this plot. And the issue with this plot seems to be that, yeah, as you adjust the viewer, it doesn't really reformat itself very well. And this legend is actually over something that might be important when we start looking at models level 1 predictors. And the visualization can be a useful tool, but we're not going to talk too much about it in this video for the sake of time. But really, you can just save it as an object, and it'll give you the plot even if you do that anyway. But then you can just refer to the RSquare table from the object. So I'm going to jump back over to the slides where I have this output. And so here's the RSquare table. And the way you refer to this is the rows are the different superscripts and the columns are the subscripts. So F2T would be this value, and F2B would be this value. And then we have the M row, which is the other one that we've talked about here. So that's how we use that package. And then we can also use this this framework to compare models using RSquare Change, a lot like we do when we think of RSquare Change in regular regression or delta R-square. So here I fit a model with a couple extra covariates. I have activity still, then I also have chronic pain and number of diagnoses. And I want to see, here's a summary of that model. I won't pull it up for the sake of time, but we'll look at it in lab. And so I can compare them using the R2 MLM function. And again, this will give you a plot too when you call it, and a couple other things that we're not too interested in right at the moment and that seem a little buggy, but the actual R-squared differences table is what we want. And so here what we have note that we have model A and model B. So first is model A and second is model B. So I have the reduced model first and the full model second. And then this gives me model B minus model A. So it's the second model minus the first model. And so here we have the change in R-square F2 total, the change in R-square F2 between. And those are the two we're going to mostly be interested in here. And we'll go into some more detail about this when we look at it together.